Welcome to Lesson 1.4, Extrema and Average Rates of Change. We're going to analyze the increasing and decreasing behavior of some graphs. So we have our first graph, which is f of x equals x squared minus 4. And we want to estimate intervals to the nearest 0.5 unit on which the function is increasing, decreasing, or constant. Support the answer numerically. Well, if we're looking at our graph, we can go and say, well, about right here is where we're having a change. Before that point, we are decreasing, and after that point, we seem to be increasing. So, from negative infinity to 0, we're decreasing, and from 0 to infinity, we're increasing. Now we're going to create a table that's shown below using x values in each interval. So we start at -3, -2, -1, 0, 1, 2, and 3, and find the values of the function. At -3 it's at 5, at -2 it's 0, -3 at -1 it's at -3, 0 it's -4, 1 it's -3, 2 is 0, and 3 is 5. The table shows that as x increases from a negative value to 0, f of x decreases. And as x increases from 0 to the positive values, f of x increases. This supports our conjecture. Okay, let's look at another graph. And we see we have a little bit of up and down motion here. So we see that about right here, we're decreasing until we get there. Then we're increasing until we get here. And then we go back into decreasing mode. So from infinity to about 0.5, we are decreasing, and from 0.5 to negative 0.5, to 0.5, we're increasing, and then after 0.5, we're decreasing again. So let's check that out using a table. Okay, again, our graph, we can estimate that f is decreasing from negative infinity to negative 1/2, increasing from negative 1/2 to 1/2, and decreasing on the interval from 1/2 to infinity. So we now are going to look at the table. We've got three tables because we have three intervals, from negative infinity to 1/2, from negative 1/2 to 1/2, and from 1/2 to infinity. We plug some numbers in, -3, -2.5, -2. And as we look at our table, we can see as we're coming in from negative infinity, our numbers are getting smaller and smaller for our f of x until we get down to 0.5. So we can see it's decreasing over that interval. Now we look at our other intervals starting at negative 0.5, and it starts increasing from there, going from negative 0.375 to positive 3.75 at where x is 1/2. So we see an increase in that interval. Now looking at after 0.5, we see that 0.5, it's at 3.75, then we see it steadily going down and down and down, and it's going towards negative infinity. So our conjecture that we previously made about it is decreasing over the interval from negative infinity to 1/2, it's increasing from negative 1/2 to 1/2, and it's decreasing again from 1/2 to infinity. Now we're going to look at extrema, and we're going to estimate and identify extrema of a function. Estimate and classify the extrema to the nearest 0.5 unit for the graph of f of x. Support your answers numerically. Okay. As we look at it, it looks like it has a relative minimum at -1. That means that's as far as the function goes down, that's not going towards infinity. and we have a relative maximum at about 2. Now remember, we're counting by 2's on this, and that's why the first one we said was at -1/2. Okay, so we'd look like we have our 2 extrema. One is the minimum and the other is the maximum. And we can tell that it has no absolute extrema because of the going towards positive infinity and going towards negative infinity. And here we see the analysis that we just spoke about. Okay, here's our support for our analysis. We're going to choose values of x in half-unit intervals on either side of the estimated x value for each extrema, as well as one very large and one very small value for x. And we're talking about -100. That's a very small value for x, -100, and +100, a very large value for x. Then we're going to look around the points, which were -1 and +2, and see what's going on. Well, at around -1, that's -1.5, -1, and -0.5. We see we have it going down to 0.7 or -7, and after that it goes back up. So we do see that at -1 it looks like it is a minimum. And we do the same thing on the other side. We have our little interval from 1.5 to 2.5, and we see we're going up to where 2 looks like the maximum. And because f of -1.5 is greater than f of -1 and f of -0.5 is greater than -1, there is a relative minimum in the interval from -1.5 to -0.5, near -1. The approximate value of this relative minimum is f of -1 or -7. We can use a graphing calculator to approximate to the nearest hundredth the relative or absolute extrema of f of x is equal to x to the fourth minus 5x squared minus 2x plus 4. State the x values where they occur. All I do is put the function into my calculator in the graph and then adjust the window as necessary so I can see all of the behavior that's visible. From the graph of f, it appears that the function has one relative minimum in the interval from -2 to -1 and an absolute minimum in the interval from 1 to 2. Here's our relative minimum and here's our absolute minimum. And one relative maximum in the interval from -1 to 0 of the domain, and that would be this one right here. The end behavior of the graph suggests that this function has no absolute extrema. Now, looking at the graphing calculator, using the minimum and maximum selection from the calc menu of our graphing calculator, you can estimate that f of x has a relative minimum of 0.80 at x is equal to -0.47 and an absolute minimum of -5.51 at x equals 1.67, and the relative maximum of 4.2 at x equals -0.2. And we can see that information right down here. Here's my x value, and there's my relative minimum. There's my x value, there's my absolute minimum. There's my x value, and there's my relative maximum. Next, we're going to look at a real-world problem. Advertisements for a new car claim that a tank of gas will take a driver and 3 passengers about 360 miles. After researching on the internet, you find the function for miles per tank of gas for the car is f of x is equal to -0.025 x squared plus 3.5x plus 240, where x is the speed in miles per hour. What speed optimizes the distance the car can travel on a tank of gas? How far will the car travel at that optimum speed? We want to maximize the distance a car can travel on a tank of gas, so we're going to graph the function f of x is equal to negative 0.025x squared plus 3.5x plus 240 using a graphing calculator. Then use the maximum selection from the calc menu to approximate the x value that will produce the greatest value for f of x. And here we see we found the greatest value right here, which is at 0.69999988, and y is equal to 362.5. Now, we need to discuss what that means. Okay, what that means is the graph has a maximum number of miles. And our maximum number of miles that we can drive is 362.5 miles. 362.5 miles. Okay, and the approximate speed oh, that's not very good. Speed, S-P-E-E-D, is 70 miles per hour. Okay, so that means that to maximize the distance the car can travel on a tank of gas, we would need to be driving 70 miles per hour, and that would take us a distance of 362.5 miles. Next, we want to find average rates of change. To find the average rate of change of the function f of x is equal to negative 2x squared plus 4x plus 6 on the interval from negative 3 to negative 1. We use the slope formula to find the average rate of change of f on the interval from negative 3 to negative 1, which means I'm going to do f of x of 2 minus f of x of 1 and divide it by x of 2 minus x of 1. That means I'm going to substitute in negative 1 into the function, negative 2x squared plus 4x plus 6, and then I'm going to plug in negative 3 into the function, negative 2 times negative 3x squared plus 4x plus 6. Okay, once I substitute everything in and get my numbers and evaluate negative f of negative 1 and f of negative 3, I find out what the average rate of change is. And as we can see, after doing all the arithmetic, our average rate of change is 12. Well, the average rate of change on the interval from negative 3 to negative 1 is 12. The graph of the secant line supports this conclusion. Okay, let's try another one. We want to find the average rate, same function, but our interval is changing from 2 to 5. We plug it in just like we did on the previous one, do all of our arithmetic, and when we simplify, we see that we have negative 10, which means I'm going to have a line that's going down. My secant is going to be going in the negative direction. The average rate of change on the interval between 2 and 5 is negative 10. The graph of the secant line supports this conclusion. Okay, now we're going to use that into a real-world problem. The formula for the distance traveled by falling objects on the moon is d of t is equal to 2.7 t squared, where d of t is the distance in feet and t is time in seconds. Find and interpret the average speed of the object for the time interval from 1 to 2 seconds. So we plug into our formula d of t sub 2 minus d of t sub 1 over t sub 2 minus t sub 1. Our interval is from 1 to 2 seconds, so we plug in 2 for t of 2 and 1 for t of 1. We do all of our math by plugging it into our d of t, and we find that it's 8.1. And that means 8.1 feet per second. So our average speed of the object for the time interval from 1 to 2 seconds is 8.1 feet per second. Okay, let's try one more. Again, we're using the same formula. The only thing that's different is we're looking at the interval from 2 to 3 seconds. So we're going to be plugging in 2 and then we're going to plug in 3 into our function. When we simplify, we find out we get 13.5 or 13.5 feet per second. That is our average speed in the interval from 2 to 3 seconds.